Welcome to my brand new guitar couch. It's not that crummy old white one anymore, and I get guitars behind me, so it's better in every conceivable way. And to celebrate my new couch, I want to make a video that I've been wanting to do for a while. It's about harmonics. Well, if you don't know what harmonics are, let's do a quick demo just to introduce the concept. Imagine this rope is your guitar string. We're going to swing it around like a jump rope. Now, I know your guitar string doesn't move like this. It's more like a, bowling. But don't worry. Pretty much all oscillators follow the same basic rules, which means the principles that we're going to talk about with guitar string also apply to water waves, pendulums, the electromagnetic waves of light and radio, even the probability waves of quantum particles. So, sorry, you're going to learn some science today. When you understand the guitar string, you will also understand a lot more of the universe. Told my mom it wasn't a waste of time. So we're going to get this swing in here. Now, one term I'd like to say right now is the wavelength, which is basically the distance from my hand right here to where I have it attached to my shelf. The shorter the wavelength, the higher the pitch of the sound, all things being equal. As long as I keep the same amount of tension on this rope, it should always swing at the exact same frequency, which is how many times it goes through 1 revolution per second. If I keep the same tension, like in your guitar string, unless you have a really bad guitar, we need to create different pitches. So how do we do that? Well, you shorten the wavelength. It spins a lot faster over here, spins a lot slower over here. But this is not the only way that the string can oscillate. Now what we can do here is try to get it oscillating like a figure-8 pattern. There we go. This shape is called the first harmonic. There's one spot in the middle that shouldn't really move much, and then there are 2 waves, each of 1/2 the original wavelength. Now, since the shorter the wavelength, the higher the pitch, this is going to, if your guitar string oscillates like this, it's going to create a higher sound. In fact, it will create a sound exactly 1 octave higher. There we go. Here's the second harmonic. The second harmonic will divide the string into 3 different sections. It's got 2 nodes where it shouldn't move very much if I do a good job. And it's got 3 waves, each 1/3 the original wavelength. So your guitar strings should vibrate in a very similar way to that rope. If you pluck it, especially in the middle, it's going to vibrate in the fundamental wavelength. If you lay your finger just lightly, exactly half the way through, which will be at the 12th fret, you can get it to vibrate in that figure-8 pattern, or at the second harmonic with 1/3 of the wavelength, and an infinite amount of other ones, though they become harder and harder to play. Is that right? Is the 12th fret exactly halfway? Is the 7th fret exactly 1/3 of the way? Well, I've never been much to just do what I was told, so let's use some science and find out ourselves. Now I've got my science tools. If you want to do this at home, here's a couple tools you're going to need. Notebook and pen. To do all science, you need to take notes. A Sharpie. No science is done without Sharpie. I've worked in a lot of different labs in a lot of different places. Sharpies are a critical tool. Now, we do not want to draw all over my Godin. Hello, Willow. You're here for my video? So that I don't mark up my nice guitar, I got this special masking tape for delicate surfaces. I would not recommend using regular masking tape. And most importantly, we're going to need some kind of measuring implement. I got this at Lowe's, I think, for $5. Make sure that it has metric. You do not want to be, we're going to have to do some math later. You do not want to have to be stuck doing math with standard measurements. It's ridiculous. Let's start this experiment by protecting my guitar with some of this masking tape. I'm going to need to mark it at the 12th fret, or around the 12th fret. I will tell you where we're marking it once we get an accurate measurement. That looks pretty good. Okay. We should be pretty protected. Now let's get out our measuring stick. And you're going to measure the exact length of the string from the nut to the bridge. And this looks like 653. Almost exactly. What is exactly 1/2 of 653? I don't know. Let me get a calculator. All right. 653.0 divided by 2 is 326.5 millimeters. Now let's take a measurement of that. 326.5. 326.5. Oh, that is exactly at the 12th fret. Well, as precisely as these tools will allow, but you know, how close are you going to get with your fingers anyway? All right, well, let's check the second harmonic. That will be exactly 1/3 of the original wavelength. 653.0 divided by 3 is 217.7, so about 218. Let's call it that. Now remember, we measured this with 3 digits of precision, 653, which means we only can reasonably say we have 3 digits of precision after any kind of mathematical process. So we're going to make this 218 millimeters, and that is correct. That is the correct measurement. You don't get more accurate just because you're divided. Let's see where 218 is. 210, 220. Well, dang it. That's almost spot on the 7th fret. Okay. It's going well so far. Let's continue to measure. The third. A good way to remember your harmonics is to add 1 to them. So the first harmonic is the wavelength divided by 2. The second harmonic is the wavelength divided by 3. The third harmonic is the wavelength divided by 4. So let's do that. 653 divided by 4 is 163.3. Round that to 3 significant figures is 163 millimeters. And we'll mark that. My guess is this is going to be spot on too. One, 2, 3, 4, 5, 6. Yeah. Right at 163. Well, so far, our teachers haven't really lied to us. Play the first harmonic on the 12th fret, the second harmonic on the 7th fret, and the third harmonic on the 5th fret. Okay, well, what about the 4th fret? Yeah, spoiler alert, there's a problem. So, 4 plus 1 is 5. The wavelength is going to be divided by 5. So, 653.0 divided by 5. It's going to give us 130.6. Get that to the closest millimeter is 131. Where is 131? Here is 130. Here is 131. That is not significantly close. In fact, the 4th fret appears to be at 135. This is 4 millimeters different. Now, I don't care how fat your fingers are, 4 millimeters is a pretty significant difference. And placing your finger where it's supposed to go versus where it should go can make a huge difference, especially with these hard, higher harmonics. Let's keep going. You know, as long as we made it this far, let's keep going. Let's see what other sacred cows we can slaughter. Let's do some quick calculations. That's probably plenty. Let's mark these. All right, here's our 131. Next is 109. Next is 93.3. I'm not really going to be able to get 3, so we'll just estimate. 82. And 73. Okay, let's see how they compare with the frets. Here's our 4th, which is significantly before the 4th fret. Our 5th harmonic is significantly after the 3rd fret. Our 4, 5, 6, 6th harmonic, about 2/3. 7th harmonic, about 1/3. And the 8th harmonic, well, that's almost spot on the 2nd fret. It is a hard one to play, so you're probably not going to use it a lot, but still good to know. So hopefully what we've demonstrated is that all of the books and websites and teachers that tell you that there is a 4th fret harmonic, well, it's a good rule of thumb, I suppose. It's a good way to remember it. You don't want to confuse a beginner by saying, well, it's like the 3rd and 0.8 harmonic. So you just say 4th. But if you want to be an expert at and play your harmonics as good as possible, remember, 4th fret, just a little behind it. And it's going to play so much easier for you. And also the 3rd fret, if you like to go so far, not quite the 3rd fret, a little past the 3rd fret. It's that easy. And all it took was some science.